Have you ever wondered why hot things glow? I mean, really thought about it. You see it everywhere. A blacksmith's forge, the filament in an old light bulb. They start glowing red, then orange, then bright white hot. Seems pretty straightforward, doesn't it? Well, it turns out that at the end of the 19th century, this simple question almost broke physics. I mean, completely. It led to a crisis so deep, they actually called it a catastrophe. So yeah, let's dive right into that.
All right, so here's our game plan. First, we're going to look at this classical catastrophe, how doing all the math perfectly led to an answer that was just complete nonsense. Then we'll get into the act of desperation that changed everything. We'll see how it managed to tame this impossible idea of infinity. And stick around, because the best part is at the end, where we'll see how this one little fix accidentally stumbled upon one of the biggest, weirdest mysteries about reality itself.
Okay, so to really get to the bottom of this, physicists knew they couldn't just study any old glowing object. They needed a perfect test case, an ideal scenario. So they came up with this theoretical object called a black body. The plan was simple. Take all the trusted laws of physics, electromagnetism, thermodynamics, the heavy hitters, and use them to predict how this perfect object should glow. And the result? Oh, it was an absolute disaster.
So you might be wondering, how do you even make a black body? It's not as simple as just painting something black, not at all. The real trick, and it's a clever one, is to imagine a hollow furnace or a box, heat it up so it's all one temperature inside. Then, you drill a tiny, tiny hole in the side. Now think about it. Any light that goes into that hole gets trapped. It just bounces around and around inside until it's completely absorbed. So that little hole is, for all intents and purposes, a perfect absorber. And here's the kicker. A neat little rule in thermodynamics says that a perfect absorber is also a perfect emitter, which means the light shining out of that little hole. Well, that's the purest blackbody radiation you could ever hope to see.
And this brings us to a super common misconception. The name black body is honestly a little misleading. It's not about being physically black. It's all about being a perfect absorber and emitter of thermal radiation. For example, our sun, which is about as far from black as you can get, is actually an almost perfect black body. And get this, even you, right now, are glowing away in the infrared, acting as a pretty decent black body. Weird to think about, right?
So two brilliant physicists, Lord Rayleigh and James Jeans, came up with what they thought was a foolproof recipe. Step 1. Count all the possible ways light can bounce around inside our hot box, all the possible standing waves or modes, and it turns out you can cram way more high-frequency, short-wavelength waves in there than long ones. Okay, simple enough. Step 2. Use a cornerstone of classical physics, the equipartition theorem. It basically says that when things are in thermal equilibrium, the energy gets shared out equally among all the possible modes. Every wave gets its fair share. Sounds logical, right? Simple, elegant, and as it turned out, catastrophically wrong.
So what happens when you put those two perfectly logical steps together? You get something called the Rayleigh-Jeans law. And look, for low frequencies, for red light, it works pretty well. It matched the experiments. But, and this is a huge but, when you look at higher frequencies, as you move up towards ultraviolet light and beyond, the prediction just goes crazy. The energy doesn't just get big, it goes straight up to infinity. You have an infinite number of possible high-frequency waves, you give each one a little slice of energy, and boom, infinity energy.
Now, I want you to really appreciate how wrong this was. This wasn't just a small rounding error. This was completely, utterly absurd. This prediction meant that every warm object, right now, should be blasting out an infinite amount of energy. Your warm cup of coffee? It should be a lethal inferno of X-rays and gamma rays. This spectacular failure became known, quite appropriately, as the ultraviolet catastrophe.
So, physics was completely stuck, a total brick wall. The same beautiful theories that could predict the motion of planets and explain electricity were now spitting out pure nonsense. This is where, in the year 1900, a German physicist named Max Planck enters the story. He realized that if the old rules weren't working, maybe one of the rules, one of the most fundamental, basic assumptions everyone just took for granted, had to be broken.
And listen to his own words about it. He called it an act of desperation. This wasn't some calm, thoughtful stroke of genius in a quiet study. This was a man backed into a corner, fighting a problem that made no sense. He said he had to find a solution, at whatever cost. He wasn't trying to spark a revolution, he was just trying to make the math work, even if it meant trying something really, really weird.
So what was this radical, desperate idea? Well, up until this point, everyone, and I mean everyone, assumed energy was continuous. Think of it like a ramp. You can be at any height on that ramp, no problem. Planck's idea was to say, no, what if energy isn't a ramp? What if it's a staircase? He proposed that energy is quantized. It only comes in discrete, chunky packets. He called them quanta. It's like money. You can have $1 or $2, but you can't have $1.37. It comes in chunks. You can have 1 packet or 2, but never, ever half a packet.
And he gave it a beautifully simple rule. E equals h nu. The energy, E, of one of these packets is directly proportional to the frequency of the light. That's the Greek letter nu. And that little h in there, that's the magic number, a new constant of nature we now call Planck's constant. But here is the most important part of this rule. It means that a packet of high-frequency, high-energy blue light is worth more than a packet of low-frequency, low-energy red light. The cost of an energy packet depends on its frequency, or its color. Okay, so energy comes in lumps. How on earth does that fix a problem with infinity? It seems totally unrelated, right? Well, the answer is just beautiful, and it's all about, of all things, economics.
Let's break this down. Think of the thermal energy in the hot box as a budget. It's only got so much to spend. Now, for the low-frequency modes, the red light, the price of a single energy packet is super cheap. It's like penny candy. The system has plenty of budget to buy lots and lots of these packets, so many, in fact, that it basically looks continuous, just like the old classical theory said it should. But what about the high-frequency modes, the ultraviolet light? Well, their energy packets are incredibly expensive. We're not talking penny candy anymore, we're talking luxury cars. The system looks at its budget and says, I can't even afford one of those. So those high-frequency waves don't get excited, not because they're impossible, but because they are just too darn expensive. They get frozen out of the picture. And this is the formula that came out of it, Planck's law. Now, don't worry about memorizing this thing. Just look at what's inside. You see that h? That's Planck's constant. And see that exponential term in the denominator? That's the secret weapon. For high frequencies, that term blows up, it gets enormous, and it just crushes the whole expression down to 0. It's a built-in kill switch for the infinity. And the result? It wasn't just good, it matched the experimental data perfectly across the board. But here's where it gets even cooler. Planck's idea didn't just solve this one big, annoying problem. It turned out to be a kind of master key. Suddenly, a bunch of other laws about radiation that physicists already knew but didn't really understand how they connected, all just clicked into place. They were all just consequences of this one, deeper quantum idea. Take 2 examples. There was something called Wien's displacement law. It perfectly explains why hot things change color from red to orange to white. Well, it turns out that's just what happens when you find the peak of Planck's new graph. Then there was the Stefan Boltzmann law, which tells you how much total energy something radiates. And guess what? That's just what you get when you calculate the total area under Planck's curve. 2 big, separate laws, suddenly explained by one single, elegant idea. And you see this in action all the time. This is why a piece of iron in a forge goes from a dull red glow to a bright orange and then to a brilliant yellow-white. As the temperature goes up, the peak of that energy curve shifts to higher frequency, bluer light. It's also how we can tell the temperature of distant stars, including our own sun. We just look at its color, find the peak of its black-body curve, and that tells us its surface is about 6,000 Kelvin. And this same basic idea allows us to make what is, I think, one of the most incredible measurements in all of science. You see, the entire universe is filled with a faint glow, the leftover heat from the Big Bang itself. It's called the cosmic microwave background, and when we measure it, we find it is the most perfect blackbody spectrum ever observed. By finding the peak of that curve, we can take the temperature of the entire universe, and it's a very chilly 2.725 Kelvin.
Now, it's funny, Planck himself was pretty conservative about this. He thought he'd only found a weird rule about how the atoms in the walls of the box could absorb or emit energy. He still believed that light itself, out in the open, was a smooth, continuous wave. But then, a few years later, a young patent clerk named Albert Einstein looked at Planck's math and had a much more radical thought.
Einstein basically asked, okay, but what if Planck didn't go far enough? What if it's not the emitters that are quantized? What if the light itself is quantized? What if light doesn't travel as a wave at all, but as a stream of actual particles, these little bullets of energy that we now call photons? And to test this crazy idea, Einstein did something absolutely brilliant. He decided to look at the noise predicted by Planck's formula. You know, the tiny random jitters in the energy field? It's like listening for static on a radio to figure out how the broadcast works. And by digging into the mathematics of that noise, he pulled out this incredible formula, which describes how much the energy fluctuates.
And what he found was just mind-blowing. The formula had two completely different parts. The first term, that's exactly the kind of fluctuation you'd get if light was made of tiny, discrete particles, like rain hitting a roof. It's a particle signature. But the second term, that's the signature of interfering, continuous waves, rippling and combining. The math was screaming that light was both, at the same time, in the same equation.
This was the deep insight. This was the moment. Hidden inside an equation that was created just to fix a technical problem about glowing ovens was the very heart of quantum mechanics. It was the first hard mathematical proof of the central mystery of the quantum world, wave-particle duality. That somehow light is both a particle and a wave. The catastrophe didn't just get solved, its solution cracked open the door to an entirely new and much weirder reality.
So, in the end, Planck's active desperation completely changed how we see the universe. It taught us that at the most fundamental level, reality isn't a smooth ramp, it's a staircase. Energy comes in steps. Which leaves us with a huge, lingering question, doesn't it? If energy is lumpy, what else is? What other parts of our smooth, continuous world are, when you look closely enough, actually made of tiny, distinct, indivisible pieces? And that is the true legacy of Planck's quantum leap.